Section 3.4, linear programming. Linear programming sounds really high level, but I actually think it's quite fun. We have 4 vocabulary words. Another one of them is the 4th one's gonna show up in a few more slides, but first 3. Linear programming is a method of finding a maximum or minimum value of a function called constraints. A constraint is one of the inequalities in a linear programming problem. Feasible region is the solution to the set of constraints shown as a graph. So think about last section. We were graphing quite a few problems together, shading everything, and we had an area where all the shading overlapped. That's your feasible region. And the feasible region is built by quite a few constraints, and the constraints are the inequalities. And the linear program in general is we're going to use that feasible region and the constraints and an equation to find a maximum or minimum value. So graphing is really, really important, and you have to be careful and you have to be neat and orderly. Okay, first example, graph the feasible region for the following constraints. I'm going to do the first one in red and see if that helps our clarity. X is greater than or equal to 0. If you remember, this is X. Okay, let me draw a thick XY axis. Okay, that's our y-axis, and that's our x-axis. We're only dealing with the positive here. So x is greater than 0 is actually, this is x is equal to 0. Draw a red line over my y-axis. So x is greater than 0 is everything bigger than this red line that I drew. This red line is x is equal to 0. Okay, let's try the next one in orange. Y is greater than 1.5. Let's draw y equal to 1.5. There is y 1.5, so it's a line going this way. And y is greater than 1.5 goes like that. Okay, the next one. Let's try it in blue. 2.5x plus 5y is less than or equal to 20. Again, x and y-intercepts are the easiest way to graph these things. So I'm going to find my x-intercept, so y is 0. 2.5x plus 5 times 0 less than or equal to 20. Sorry, when we find our intercepts, these can be equal to 20. So solve for x, divide by 2.5, divide by 2.5. X is 8. Solve for y. Our y-intercept is where x equals 0. So 2.5 times 0 plus 5y equals 20. Y equals 4. Okay, x equals 0. I'm sorry, goodness, did I do that? X equals 8. I don't know why I put 0. So these are our x-intercept and our y-intercept. X equals 8. 1, 2, 3, 4, 5, 6, 7, 8. Put a dot. 1, 2, 3, 4. 1, 2, 3, 4. Put a dot. And draw a straight line. Okay. I don't know if it's greater than, less than. Put in a test point. 0, 0. Running out of space. 0 plus 0 less than or equal to 20. Is 0 smaller than 20? Yes. So we're shading down. Okay, let's try the next one. 3x plus 2y less than or equal to 12. You're going to be working on your paper a little bit more than I'm working here. I'm going to try it up here. Our x-intercept, y is 0. 2 times 0 equals 12. Divide by 3, x equals 4. Okay, that's our x-intercept. Our y-intercept, x equals 0. 2 equals 12. Y equals 6. So graph it. X equals 1, 2, 3, 4. y equals 1, 2, 3, 4, 5, 6. Draw a straight line. And put in our test point of 0, 0, 0 plus 0 less than or equal to 12, which is true. So we want to include 0 in our shading. Okay, this is where you guys with pencils will be a lot better off than me on an iPad. So it looks like we want everything bigger than this on the red line, smaller than the green, smaller than the blue, and bigger than the yellow. So it looks to me like our shading, which we'll do in purple, is going to be in this area right here. Okay, that took 5 minutes. Word problem. Don't groan. They're fun. Yum's Bakery bakes 2 breads, A and B. One batch of A uses 5 pounds of oats and 3 pounds of flour. One batch of B uses 2 pounds of oats and 3 pounds of flour. The company has 180 pounds of oats and 135 pounds of flour available. Write the constraints for the problem and graph the freezable region. I see the equal to part, 180 and 135. So we're going to let X equal bread A, the numbers for bread A, and Y equal the numbers for bread B. So we have 5X, which is right there, because that is oats, plus 2Y, that's oats, so 5 pounds of oats for batch A, bread A, 2 pounds of oats for bread B, and that has to be smaller than or equal to 180 because they only have 180 pounds of oats. Let's look at the flour. 3 pounds for bread A, right there, and 3 pounds for bread B. They only have 135 pounds of flour. Those are your constraints. The other ones are bread A has to be equal to or greater than or equal to 0. Bread B has to be greater than or equal to 0. We're going to graph our feasible region. Excuse me. X is greater than 0 and Y is greater than 0 is easy. So X is greater than 0 is, remember, everything going this way. Y is greater than 0 is everything going this way. Let's do our 5x plus 2y less than or equal to 180. Our x-intercept, y is 0. So 5x, y is 0, so I'm not going to write that one down. Divide both sides by 5, and 180 divided by 5 is 36. X equals 36. Our y-intercept, x is 0. So 2y equals 180. Divide both sides by 2. Y equals 90. Okay, I'm going to push pause and graph those. I have to figure out my scale, which is hard. Okay, I got my y-intercepts, and my scale is going to be by tens. So 5x plus 2y is less than 180. If I put in my test point of 0, 0, I need to shade underneath it. And let's try our next one. Our x-intercept is 3x equals 135. 135 divided by 3, x equals 45. Y-intercept, x is 0. 3y equals 135. Divide both sides by 3. Let's plot them. 10, 20, 30, 45. 10, 20, 30, 45. I'm graphing everything underneath. So I guess I'll just change to purple again. I'm less than the red line, less than the orange line, and in the positive quadrant. So cut it right there. And that is my feasible region. All right, you guys try this one. All right, there you go. Everything's colored and my feasible region is in purple. All right, in most linear programming, you want to do more than identify the feasible region. Often you want to find the best combination of values in order to minimize or maximize a certain function. This function is the objective function. It's an equation, guys. The objective function may have a minimum, a maximum, neither, or both, depending on the feasible region. We have a difference between bounded feasible regions. That means all of my sides have a line. Everything is bounded. There aren't any openings. Nothing's left open. Like here, I have an opening and an opening. It's unbounded. This is funny, I think. More advanced mathematics can prove that the maximum or minimum value of the objective function will always occur at a vertex of the feasible region. Okay, you have a graph, you've shaded it. Okay, your vertexes are the corners, the edges. All right? If an objective function has a maximum or minimum value, it must occur at one or more of the vertices of the feasible region. So when we graph, we're going to find the ordered pair of each vertice. All right, example 2. Solving linear programming problems. Yum's Bakery wants to maximize its profits from bread sales. One batch of A yields a profit of $40. One batch of B yields a profit of $30. Use the profit information and the data from example 1, the one we just did, to find how many batches of each bread the bakery should bake. We're going to say P equals profit, and this is the equation that we just came up with using this information. Okay, 40x, which is A, plus 30y is our profit. Recall the constraints in the graph from example 1. This is what we graphed, and I've highlighted the vertices. Now we need to come up with the ordered pair for each vertice. This first one, it looks like it is x is 0, y is 45. This next one, 0, 0. Down here I have, let's see, 30, that was the 36 one, if you can look back at your notes. And this one right here, if I read the graph, it's 30, 15. This is why accuracy in a neat graph is so important. So I've just listed my vertices. What I'm going to do is use my profit equals 40x plus 30y and my vertices. I'm going to list them smallest to biggest. I'm going to plug in x and y for my equation. Okay? 40 times 0 plus 30 times 0. My profit is 0. Not very maximized. Okay. 40 times 0 plus 30 times 45. That gives me a profit of $1,350. 40 times 30 plus 30 times 15 gives me a profit of $1,650. 40 times 36 plus 30 times 0 gives me a profit of $1,440. Okay, the problem said to maximize the profit, which is this right here. So to maximize the profit, we should bake 30 batches of A, 15 batches of B, and we will have the most profit that we can get. All right, solving linear programming problems. Maximize the objective function. And we already graphed this, so I'm going to go ahead and graph that again. You can look at your notes. Okay, there's the graph. I'm going to highlight our vertices so it's easier to read. Okay, our vertices, I'm just going to list them off. The first one right here, x is 0, y is 1.5. Directly above that, x is 0, y is 1, 2, 3, 4. Next one over, I have x 1, 2, y 1, 2, 3. And then x 1, 2, 3, y 1.5. I'm going to copy that over to the next page. Okay, let's go ahead and plug them in. 25, 0 plus 30 times 4. 25 times 0 plus 30 times 1.5. 25 times 2 plus 30 times 3. 25 times 3 plus 30 times 1.5. Alright, if you remember, it said to maximize it. So our maximum for this equation is at 2, 3. Now, if you had a minimum, you'd be looking for your smallest number, but it's been asking for maximums. So our minimum would be 45, and it would occur at vertices 0, 1, 0, and 1.5. That's it for today.